So now we're going to look at what happens to the clearance of inulin, glucose, and pH when we increase the plasma concentration to very high levels. So let's start with inulin and remind ourselves that the clearance of inulin is equal to the GFR. You can see over here that 120 mils of plasma was filtered, and then once we have the processes of the kidney occur, we reabsorb water, and you end up excreting urine and a urine volume of V dot. Notice that the same two inulin molecules that are being excreted here were the same two molecules that were filtered. And so 120 mils here is empty, has no inulin in it, and that represents the GFR. So to refresh our memory, right, we have the urinary excretion of inulin is equal to the amount that was filtered, which is going to be P inulin GFR. Okay, it's not handled by the kidney in any way, and that's all we have to consider there. And we divide both sides by P inulin. All right, and we end up with the clearance of inulin is equal to GFR. So now the question is, what happens when I increase the plasma concentration of inulin? So X is going to be whatever the substance may be. So in this case, it's inulin. And we know we're starting at GFR, but what happens when I raise the inulin concentration? Well, if I raise the inulin concentration, what's going to happen is I'm just going to filter more inulin. It's going to go up to the same degree. And so if I have 4 inulin molecules coming in here because I have a higher concentration, there'll be 4 in the urine. If I have 10 being filtered, I'd have 10 in the urine. If I have 10,000 inulin being filtered here, I'd have 10,000 in the urine. So there's no saturation of transporters possible because there is no transport of inulin to begin with. So as long as the concentration goes up and the kidney's not affected anyway, and we wouldn't expect it to, you're just going to excrete that extra amount of inulin. So this is going to be just a straight line, unaffected. And again, the reason for that is if I increase this, right, I'm increasing the amount filtered. And remember, the P inulin is part of the amount filtered. The GFR is a constant when you're considering this experiment. Changing the plasma inulin concentration shouldn't have any effect on the GFR. So the GFR being constant under these conditions means that those are just going to go up the same, which means the clearance is going to be the same. So that's inulin. Let's talk about glucose. So remember, glucose, under normal conditions, I reabsorb all the glucose as long as my glucose concentration isn't too high in the plasma. And over here we saw that those 2 glucose molecules were coming back. I restored the 10 that came in, and there was no volume here that was devoid of glucose. It's 0 excreted in the urine, and so the clearance was 0, right? So remember, that was the U glucose V dot equaled 0. Okay, and that's where we were. So we can even make these X's if you want to highlight that. Now, once the glucose concentration is high enough, that is when the transporter cannot further increase the glucose transport, and now it's maxed out. It's reached its tubular maximum. So this isn't going to be all that helpful here, because if I divide both sides by plasma glucose, and I get my clearance of glucose equals 0, that's fine to show that the clearance is 0, but how are we going to illustrate this mechanism of saturation of the transporter? So let's represent the excretion of glucose a different way. Okay, let's say that the glucose excretion is equal to 2 things. It's equal to the amount that was filtered. Okay, so that would be the plasma glucose times the GFR. So I had 2 molecules here. Okay, so there was 0 here. So 0 equals 2 molecules that was filtered, but I need to subtract how much glucose was reabsorbed right here. That's the reabsorption of glucose, right? Or the transport of glucose. So if you want to use T for transport, that's fine, or R, doesn't matter. But I have to subtract the transport of glucose. All right? So if I divide everything by the plasma glucose concentration, all right, now I end up with the clearance of glucose equals the GFR, which is the clearance of inulin. So we can write clearance of inulin, they're interchangeable, minus this ratio of transport of glucose, the reabsorption of glucose to the plasma concentration of glucose. So normally, as I increase the plasma concentration of glucose, the transport should go up. And that ratio in this example would be exactly equal to the GFR, okay? But up to a certain point, whatever that plasma level is, this transport of glucose will no longer be able to increase further. It's maxed out. And so what happens then is as I increase the glucose concentration, this ratio becomes smaller and smaller and smaller. And I start to have glucose appear in the urine. All right? Now, as I go further out, the amount that you're actually reabsorbing, the ratio of T glucose to plasma glucose, that ratio, which is equivalent to a plasma volume, that is going to get such a small value that this term will just drop away, and the clearance of glucose is going to look like the clearance of inulin. Okay? And so this is going to asymptotically approach the clearance of inulin. So you see that it's increasing towards the clearance of inulin. Now, will it ever be exactly the clearance of inulin? Well, no, that's not going to be possible because there's always going to be some small amount of plasma that you have to subtract off, but it's going to get awfully close. And so it's going to look a lot like inulin because this amount that's being reabsorbed here is going to be negligible. Okay? Now let's take a look at PAH. So for PAH, we can do a similar explanation, right? So over here for the PAH, right, I have the urinary excretion of PAH. That's equal to the amount of PAH that was filtered. So that's going to be plasma PAH times the GFR. Now in this case, I'm secreting PAH, and that represents a transport in the other direction, right? I'm adding to the tubular fluid, so I'm going to be adding the transport here of PAH. So if I divide everything by the plasma PAH, I end up with the clearance of PAH is equal to the GFR, which is, again, the clearance of inulin, plus the transport of pH divided by the plasma concentration of pH. So now in this case, we know that before that the clearance of pH was equal to the renal plasma flow. Remember, the amount of pH that was coming in was 10, and then all of it got secreted. You had 2 over here that got filtered, and then 8 that got secreted, so there was 0 left over here in the renal vein. That volume, the renal plasma flow volume, was empty, right? It was cleared of cleared of PAH rather. And so in this case, while I'm starting at the renal plasma flow, and as I increase the plasma pH and I transport more, the transport mechanisms do respond to an increase in substrate up to a point. Once those transporters get saturated in the proximal tubule, now they're maxed out. And so when I reach this maximum transport rate of PAH, now this is going to start to become smaller and smaller and smaller as the plasma concentration continues to go higher and higher and higher. So under these conditions, right, if I were to represent this as these triangles, right, for PAH, it's going to start to decline like so as that ratio gets smaller and smaller and smaller, approaching the clearance of inulin, just like glucose did. Now, the difference is that you're approaching it from a higher value and it's going down as opposed to 0 and going up, but they're all converging because this term is dropping out as you go to a very, very high plasma concentration. Okay? And this illustrates another important point. Knowing that the clearance of inulin is the gold standard, equaling the glomerular filtration rate, if you have an unknown substance, if you compare that substance's clearance to the clearance of inulin, you know how the kidney is handling that substance. We know that if the substance clearance is greater than the clearance of inulin, then therefore the substance had to have been secreted. If the substance has a clearance that's less than the clearance of inulin, then the substance was reabsorbed. In the cases of glucose and pH, they're on the extremes. When I reabsorb all of the glucose, I end up with a 0 clearance. When I secrete all of the pH, I end up with a clearance that's equal to the renal plasma flow. But there can be substances that are in between. They're not 100% reabsorbed and they're not 100% secreted. So this sets the boundary points for clearance, putting inulin right where it needs to be as a good comparison molecule when you're dealing with unknown substances. And now that explains a very important concept here using this graph of the concept of saturation of transporters. And the saturation of the pH transporter is an example of saturation of a secreting transporter, and the saturation of the glucose transporter, the SGLT2, is an example of saturating a reabsorption transporter.